All right, in this video, we're going to look at a few parameterizations for some important surfaces that we're going to encounter for the remainder of the chapter. And so to begin, let's say we have a surface that's given in explicit form. So in other words, we have the surface described by the equation z is equal to g of xy, where we let x and y vary over some region R. Okay, here the idea is that since every point on that surface, which I'll call S, right, has coordinates of the form x comma y comma g of xy, what I can do is just draw the position vector that goes from the origin out to that point. And now as I let xy vary over this region R, this position vector is going to trace out the points on the surface. So in other words, these coordinates that describe locations on the surface, okay, those will become the components of our parameterization vector R. So we get that R of xy is simply x comma y comma g of xy, and we're letting xy vary over this region R. All right, so this in some regards is the simplest type of surface to parameterize. You don't really have to do any work. It just comes directly from this equation z is equal to g of xy. The downside, though, is that not all surfaces we want to work with can be represented in this form. Okay, so for example, a cylinder whose equation is x squared plus y squared is a squared, that equation cannot be written in this explicit form z is equal to some function of x and y. So how can we go about parameterizing a cylinder? Well, there we can think in cylindrical coordinates. So recall in cylindrical, x is r cos theta, y is r sine theta, and z is just itself. And if I'm on a cylinder, say of radius a, since x squared plus y squared is equal to r squared in cylindrical coordinates, I get that r squared is equal to a squared. So in other words, r is just constant a. And so now if I set u equal to theta and v equal to z, okay, I can rewrite these equations as follows. Okay, x there would be a, because again, r is just constant a on the cylinder, times the cosine of u, because I'm setting u equal to theta. So a cos u will become the I component for the parameterization. And likewise, the j component, that will come from this equation for y here. This is y is equal to, well now, a sine u. Okay, so that's our j component. And then lastly, since z is just itself in cylindrical, and we're setting z equal to v, our k component for the parameterization is just v. Okay, and to cover this portion of the cylinder, where we're going to let, say, z vary from c to d, okay, we're going to let u, which is just theta, it's just the polar angle, vary from 0 to 2 pi, and v, which again is just z, that's going to vary from c to d. All right, so not too bad there. Let's go ahead and look at cones next. So again, we can think in cylindrical here. So um, now note that since x squared plus y squared is r squared, on the cone, we get z squared is equal to r squared. So in other words, z is just equal to r on the cone. So again, if I set u equal to theta and v equal to z, these equations will become the following. Okay, so x will be, well, r, but r is equal to z, and we're setting z equal to v. So this will become v cosine of u, because again, u is theta. So v cosine u, that's the I component. And then likewise, the j component will be v sine u. And then lastly, since z is just itself in cylindrical, and z is equal to v, we get just v for the k component, just as we did for cylinders. All right, and then again, we'll let u vary from 0 to 2 pi, and v will vary from c to d. And that's going to give us this portion of the cone where z varies from c to d. All right, cool. And then lastly, on the list, we have spheres. So if we're looking at a sphere centered at the origin of radius a, while we could use cylindrical coordinates, again, it's oftentimes more convenient to use spherical coordinates. So recall that in spherical, x is rho sine phi cos theta, y is rho sine phi sine theta, and z is rho cos phi. Okay, and since rho, which is just the radial distance from the origin, is constant a on the sphere, if we set u equal to phi and v equal to theta, these equations up here can be rewritten as follows. Okay, so x will equal a, because rho is constant a, sine u, because u is phi, times cos v, because we're setting v equal to theta. So that's our I component. And then likewise, the j component is a sine u sine v. And then lastly, for the k component, since z is rho cos phi, we get a cos u. All right, and here we're going to let u, which is phi, that's going to vary from 0 to pi. So when phi is 0, recall that's when we're on the positive z-axis, and then we're going to rotate through 180 degrees. So that's when we're down here on the negative z-axis. And then v is just theta, that's the polar angle. And so that's going to vary from 0 to 2 pi. All right, great. So last thing I want to say here in this video are just two things. One, you'll notice I also included these normal vector uh, uh, calculations. We'll get into those in problem 3. The other thing I want to say here, though, is that this math3d.org does plot parametric surfaces rather nicely. If you want to add in a new parametric surface, you just click on Add Object and select Parametric Surface. So it defaults to this surface, which is just the parameterization for the cone that we just looked at. Here I put in a parameterization for cylinder. Okay, and I can slide this around and change the radius, right? So pretty nice. It's definitely can come in handy in terms of helping you visualize certain surfaces and how they intersect and all that good stuff. So, all right, we'll call it good there. In the next video, we're gonna look at parameterizing some other surfaces using a lot of the same ideas that we looked at here. All right, I'll see you there. Thanks.